So now we're going to look at reaction coordinate diagrams, which show the energy changes that take place for each step of a reaction mechanism. Right down here, we're looking at A minus B plus C, and then A plus B minus C. On the left side, we have the concentration of the reactants, and on the right side, we have the concentration of the products. At the very top, we have this thing called the transition state, which is the highest point on the reaction pathway. It is the maximum energy, and it is very unstable. Right here, all the bonds are partially broken and partially formed. And if you kind of think about it, when you have partials, they're not going to be very stable, right? They're going to be unstable. So the structure is somewhere between the reactants and products of a transition state. And then right here, in a transition state, if there's low energy, then the reaction will move forward, right? There will be products. However, if it is high energy, the reaction will not move forward. There will be no products. And then the more stable the compound is, the greater its concentration at equilibrium will be. We can tell that through K equals right here. If products are stable, the concentration of products are larger. The K equals is going to be 1, right? If we have 2 products over 1 reactants, it's going to be 2, which is greater than 1. However, if we have 1 product and 2 reactants, it's going to be 0.5, which is less than 1, right? And that answers that right there, which is if products are unstable, concentration of product is small. Oh, that is wrong. If products are unstable, that's right. If products are going to be unstable, the concentration of products are going to be small, because right here we say that the more stable the compound is, the greater its concentration at equilibrium will be. And if a product is unstable, it will be small. Right here, we have the definition for thermodynamics, and it is the relative amount of products and reagents at equilibrium. So really, it's asking how much product is formed. Gibbs free energy, right down here, can be calculated as the free energy of all products minus the free energy of all reactants. So now let's take a moment to talk about Gibbs free energy. We'll change in Gibbs free energy delta G, which is free energy of all products minus free energy of all reactants. So less free energy means more concentration. More free energy means less concentration. Okay, so over here we see that reactants have a higher free energy than products. Okay, so because the products have less free energy, that means they have more concentration. So the products are going to be the 2 over 1, which is equal to 2, which is greater than 1, right? So K equals is going to be 1, which is exergonic reaction, and delta G is negative. Because the products, right, free energy, 1 minus 2 equals minus 1 equals minus delta G, 0. Okay, because we're just assigning a fake number right here. We know that the product has a free energy that's less than the reactants, so we say that it's 1. And then we subtract that from 2 because we're assuming that it's 2 over here, and we're going to give that a negative 1. So again, less free energy means more concentration, and that way we can get K equals as well for products over reactants, and then we can also calculate delta G from that free energy. Next, on this side, we have an endergonic reaction. So there are more products, so higher free energy is going to equal lower concentration, right? And then lower free energy is going to indicate higher concentration. So product is going to be 1 over 2, which is 0.5. So actually, this note needs to be fixed, right? Products are less because higher free energy. And then reactants are more because lower free energy. And then again, it's going to be positive delta G. Okay, that looks kind of ugly. It's going to be positive delta G because we just calculate that normally. So we do 2 minus 1, which is 1. That's positive, equals positive delta G. However, products is less, reactants is more, meaning products over reactants is 0.5. And that makes it endergonic right here. So both K equals and delta G indicate whether the products or reagents are favored at equilibrium. Delta G 0 can be written as negative RT natural log of K equals. R is going to be the gas constant, which is 1.986 times 10 to the negative 3 kcal per mole. It's a K. And then T is going to be temperature in Kelvin and natural log of K equilibrium. So now we're going to look at reaction coordinate diagrams. Gibbs free energy has an enthalpy and entropy component. Delta G is Gibbs free energy, delta H is enthalpy, and delta S is entropy. And delta means change in. So enthalpy, delta H, is heat given off or consumed in a reaction. We calculate this by saying heat required to break a bond minus heat released from forming a bond. And this measure of the energy of bond breaking and bond making process that occurs in a reaction. Exothermic is negative delta H, which is when bonds formed are stronger than bonds broken, which again makes sense, right? Because in order for it to be negative, it would have to be 1 minus 2, and bonds formed, right? Endothermic is positive delta H, which are bonds formed are weaker than bonds broken, meaning it would have to be 2 minus 1, right? Bonds broken, where'd it go? Bonds broken, right? Next, we look at entropy, delta S, which is the measure of the freedom of motion in a system. Delta S is written as freedom of motion of products minus freedom of motion of reactants. It works like plus and minus, just like the other one, exothermic and endothermic. Negative delta S products have less freedom of motion than reactants. Positive delta S products have more freedom of motion than reactants. Okay, so freedom of motion means like 2 molecules of product have more freedom of motion than 1 molecule of reagent. Over here we say negative delta G makes a reaction favorable because negative delta G is gonna have more products, right? Because keep in mind what we did a couple pages before this. Negative delta G is the free energy of all products minus free energy of all reactants. Negative delta G is right here. Less free energy equals more concentration, right? And that's going to mean K equals is greater than 1, which is an exergonic reaction. And the delta G is negative, which means products are favored, right? Exergonic. And then we have positive delta S is more freedom in products, and then negative delta H is exothermic. Is generally what we want for this to be negative delta G to make the reaction more favorable. Entropy is temperature dependent and becomes more important as temperature increases. Okay, entropy is the one with the S. Delta S is endergonic reaction if delta G is positive at low temperature, and then exergonic reaction if negative delta G at high temperature. Then we look at Le Chatelier's principle, which says that if an equilibrium is disturbed, the system will offset the disturbance. So if we were to remove products, right, take out C, it forces the reaction towards the products to make more C. If we add excess reagent, like we add more B, it increases concentration of reagent and pushes the reaction towards product to balance it out. So if we increase B, it's going to go forward more to make more product so that the reagent can be balanced out.